right, so this mini lecture is going to look at the strength of charged particle fields, the force of charged particle fields in the presence of an electric field. And we're going to use a point charge producing that electric field to let us conceptualize what this force might look like, and then that we can extend to generalization. So let's say I have a positive charge Q. This positive charge Q exerts an electric field, influences the space around it. And we know from a previous mini lecture, if you haven't watched that, look at that lecture on the direction of electric fields from point charges. That field is in a direction that's radially outward. So we have this sort of starburst of electric field lines radially outward. We know that the electric field is equal to K, our Coulomb's constant, times charge Q divided by the radius squared. So wherever we're interested in the electric field, the radius, if we're interested in the electric field at this location, the radius is the distance between the charged particle and the location of the electric field. Well, now let's imagine that we're interested in a charged particle Q at this location E. Well, Coulomb's law tells us that the electric force between 2 point charges is K, Q1, Q2 over the radius squared. Well, Q1 is my positive Q. So we have K, Q. Q2 is my capital Q here. So we have capital Q. The radius is the distance between those 2 point charges. Radius squared. Now if I do a little rearranging of this equation and move my K just inside this little q, I end up with Q, and I'm going to change the color of K to blue, over Q times Q, big Q, over R squared. And what do I notice? This is the relationship for my electric field produced by charge Q at that location in space. So I can rewrite the electric force due to an electric field as Q times the electric field. And that actually is a general equation. So the force a charged particle feels by an electric field is equal to the charge of that particle times the strength of the electric field. What about the direction? Well, that's in another mini lecture that looks at the direction of a charged particle force on a charged particle in an electric field. But as a preview, if these are both positive, they're going to repel each other. Repulsion is opposite from each other, which would be along the same line as that electric field. If Q is negative, they would attract each other. Attraction would be towards the electric field, electric charge here, which would be opposite the electric field. But that's elucidated much better in its own mini lecture on the direction that the charged particles feel, the force, direction of the force charged particles feel in an electric field. All right, so the strength of that force is related to the electric field and the charge within it. Good job.